So I'm very well known for running over time, so I'm going to have my own time check here. And this thing. So for the next, I think 25 minutes or half an hour, I'm going to talk to you about a new, well, 1-year-old now, collaborative project within the Linux Foundation, codenamed FDIO, also pronounced as FIDO, a faithful doc, and talk about the universal data plane. So this slide shows really a top-level overview of what FDIO and the software that underpins FDIO is, the set of claims. There's also the agenda for the talk, and also the summary. FDIO project has started in February 2016 as a collaborative project across few vendors, service providers, and you will see the list on one of the next slides. And one of the goals was really to drive the development of the networking-centric data plane for processing packets on COTS and general-purpose computers. So the tenets of the software that is developed within the FDIO is really focusing on efficiency of processing packets. So it's all about data plane. And the claim to the fame, the sort of, we don't have any marketing guys within FDIO, so we're not very good with the taglines, but we believe that it's a very efficient software, and we put the glove out there to say it's the most efficient on the planet. And we're happy for someone to pick us up and do some bake-off testing in open source. So it's all about performance. There's also the way that the platform is developed is very modular, and I will dive into some of the technical detail on how this works. And it's a native software written for computers across different CPU microarchitectures. And hopefully, at the end of the talk, I succeed explaining on how can we get to the processing network packets, IPv4, IPv6, L2, at terabit speed on a single server. So I'm going to go quite quickly through some of the top-level overview slides of the project, and then I'm going to spend a bit more time on the technical details, explaining how the software works, and what's the magic or just the technology that's cool that underpins it. And then we will look at some results and performance results and potentially also some use cases. So it's a multi-party, multi-project. It's a project that's multi-project. So there's you will see a number of projects that are already active within the FDIO. And the focus is solely on data plane and things that are around the data plane. So it's processing packets and also the manageability aspect and usability aspect of that. It's really focusing across three, let me try to use this laser thing, 3 layers. So there is a network I/O, which is getting the packets out of the wire to the computer. It's processing the packets, which is the key core component of the system, VPP. And then there is a management agent that actually makes the system usable. In terms of how the FDIO fits in the overall stack, it basically deals with the data plane services. And also this picture is, fairly simple with some of the open source projects. If you look at the ONS presentation from last week, FDIO features there in a much more complex stack, but nevertheless it's put alongside projects like OVS or OVS DPDK. FDIO has a number of members that are sponsoring or founding the project. This includes a set of service providers. You see 2 here, some network vendors, chip vendors, and also integrators. And the main reason why we need members is to fund the infrastructure in the lab, specifically the testing and performance testing labs that are in operation within FDIO. In terms of the contribution, the number of vendors and folks and the contributors is much larger as per slide. So, if you're into numbers and you're in open source and you count how project is, what are the metrics of successful project, FDIO has been in operation for a year. And the number of commits, contributors, and organizations involved compares quite favorably with other projects that have been there for a while. In terms of the projects, VPP to drive the NICs and hardware today predominantly depend on DPDK, developed also in open source, dpdk.org, the folks that recently joined Linux Foundation. But then it includes a number of different projects, all plugging into the VPP, which is really a platform, a modular platform that provides the packet processing. And this includes things like NSHSFC1, which is a project for Lisp-based overlay VPNs, information-centric networking, and so on. And then there are agents. Vertically across those projects, there's a set of projects that drive the automation of the development. And one of them is SysIT, standing for Continuous System Integration and Testing, that I am a technical project lead for. And we do basically performance testing within that project. In terms of the stack integration, if you're into OPNFV, and I guess most, if not all of you, are from the service provider, so you're probably paying attention to OPNFV. There's a project called FDS, Fast Data Stack, that actually does the integration across the OpenStack, controller, Open Daylight, and VPP. So, the core of FDIO is VPP. VPP stands for simply Vector Packet Processing. I was already at Cisco when we were open sourcing VPP, and before VPP got open source, it had many names, and including names with quantum and all sorts of innovative names. At the end, we got back to the name that actually describes the original technology. And that's the VPP. And that's the technology that Cisco has actually developed quite a while back and shipped as an embedded subsystem as part of a number of different hardware and software systems and platforms. And it's the main contribution that Cisco did to the FDIO. And I'm going to spend now 10 minutes to talk about what VPP actually is. In terms of compatibility with CPUs, Intel x86, Xeon, Atom, then ARM and Power 8 processors. Most of the performance crunching we're doing is on Intel Xeons, and we're hoping to add Atoms and other platforms into the public labs this year. So, talking about technology. I guess most of you here are networking guys. How many are computer guys in terms of working in at detail level at the C and assembler level from the development perspective? Any computer guys? All networking? A bit? Okay. So I personally came from the networking background, and that's how I know some of you here. I built computers at the university, and really what FDIO was for me is to rediscovering computing. The way I remembered computer was something like that, an Intel 880 or Z80, an ALU, not standing for a vendor name, but for the von Neumann Turing name. A simple thing that does calculations. And it took me quite a while to realize that crunching packets is actually all about doing calculations, just doing them very fast. And they were done in ASICs in the past to get high rates, and now we actually can get quite high rates in computers, as per some of the earlier talks on 80 gig firewalls. I think we can actually do a bit better than 80 gig. So the ALUs became a bit faster. They had CPUs with a number of peripherals, and then they kept evolving. They got much faster. And the guy at the bottom is actually a modern functional block of the Xeon machine with 2 sockets and some points that I'm going to talk about later, A, B, C, D. But when you actually click on it, you will see that it is actually a bit more complex within the socket. The CPU is not an ALU anymore, it is a number of ALUs, and There is a front-end piece that works in the in order, fetching instructions, and then executes them in parallel. So quite complex. So to make it, what's important for processing packets? Working with Intel in FDIO, we identify actually 4 things. CPUs needs to be fast and executing packets. So minimize number of instructions per packet and maximize instructions per cycle for parallel execution. Memory bandwidth, well, memory is slow, so need to make a good and efficient use of that. Ideally, avoid checking memory per packet. Network I/O, clearly make sure that we leverage the full capability of I/O per CPU. And then inter-socket transactions across NUMA, just avoid them. So the answer to that in FDIO is use vectors. So here is the actual top-level functional diagram of how vector packet processing works. We have a graph of nodes that are processing packets, and there is a node per function. You can probably derive on what each of those nodes do. So we have a graph nodes. We have an input graph nodes that deal with ingress traffic from physical NICs or virtual NICs. When we get packets, we actually, instead of processing packet by packet, we're processing vectors of packets. So the vectors of packets are passed around the graph for processing and to do the work. If the vector is split, because the way the packets are they are following the same pattern, they basically split and moved around, ending up in the right endpoints. Now, with VPP, because we wanted VPP to be a platform. So we already have a modularity. We have functions written in nodes. Now, what about if you don't really care on what's already there? You know it's working. You know it's hardened. You know it's RFC compliant for the set of V4, V6 things that apply. What if you want to add your own stuff? Well, we have a concept of plugins, which are basically written and linked as share objects that do not assume any knowledge about the graph apart from only when they plug in and when they plug out. And they are basically the first-class citizens where you can write your node, plug into the graph, and do a useful work, whether it's a telemetry, whether it's a DPI, whether it's anything that you want to do in a custom fashion. And they can be built, and they are linked independently from the VPP tree. The same goes for hardware acceleration. So the same applies to the plugging the hardware acceleration drivers. So we know that we need to process packets fast, and we at 10 GiG to go at line rate, we have 67 nanoseconds to process a packet. Memory is too slow, so we need to simplify, and we have to abstract such that we don't really need to pay attention to this complex architecture of the microarchitecture of the CPU. So instead, we actually apply the vectoring and the graphing of a graph of nodes to leverage the cache architecture of the modern CPUs, keep them warm or hot, and actually do all the processing of data and instructions within the cache. And you've got a bit of the eye chart there, but basically if I summarize, with that approach, we are taking all the bottlenecks and critical resources that I have described earlier. So we're basically taking the A, B, C, D. We are efficient with the CPUs. We are hardly using any memory and per packet, and we're not using any cross-socket, and we're optimally using PCI. So how does this apply to the actual performance numbers? I want to look at some charts. Apologies for the font. Hopefully you can see it on the handouts. These charts show the testing where we connect a routing tester like Ixia, or open source tester like T-Rex, also in FDIO, to a server. This is a UCS server with 2 Intel Xeon CPUs, with 6 NICs, a total of 12 40 GiG packets, 40 GiG interfaces, and we drive basically packets at rate. And the IPv4 tests shown here are containing 1 million of IPv4 routes. These are /32 routes. For v6, it's 500,000 /128 routes. You can see that for IMIX, we are getting to the line rate of the per NIC, which is limited by the PCI bandwidth, 50 gig. But in terms of the per core performance, for 64 bytes. For IPv4, we are at 12 Mbps for the 2.3 gig CPU. For IPv6, we are at about 10 million PPS. And for IMIX and 1518, we are at rate. Moving to the L2, for those of you who love layer 2 switching or layer 2 VXLAN, the numbers also look favorable. We are line rate at IMIX and 1518 bytes packets. So we're basically driving the PCI lanes at the full speed of 50 gig for the times 8 connectivity. So performance numbers are on slides. They also tracked and published per test and per report that we issue every release, every 3 months. So they are ready for inspection and repeatability. And we're actually we're spending a lot of time to make sure that the test results we report are repeatable. And we also provide the statistical data accompanying those results. So applying this VPP as a platform with the existing feature set to some actual use cases. I'm listing 2 of them, the SD1, or basically an overlay VPN with crypto and CGNAT. We can actually look at the detail on the first one. That's the one that we demonstrated at MWC show in Barcelona on the new hardware from Intel, and it was done jointly between Cisco, Intel at their booth. So imagine you have the VPP software running as a vRouter VNF in a data center connecting a number of remote sites and running some sort of overlay, so IPsec or Lisp over IPsec. And so we did the test. We did the test on a modern computer. The CPU is codenamed SKL. I can't say the name of the CPU as it is not yet shipping, but it will ship soon, mid this year. And this CPU is special because Intel is addressing one of the big bottlenecks in Xeon CPUs, and that's the I/O bandwidth. And I will show it on the next slide on what it actually is. And we demonstrated that with these 2 servers, each having 2 sockets, we're able to pump 938 gig. This is unencrypted bandwidth, IPv4 overlay with zero packet loss. And number of interfaces, number of 100 gigis and number of 25 gigis and 10 gigis, all NICs from Intel, and the running open source software. And that's where the tagline of 1 terabit services on the single server. So why we believe it's important? Well, I like it because my lab gets upgraded mid this year to actually have those numbers published as part of just Linux Foundation FDIO release cycle every 3 months. But it is important because we are moving from Xeon that's shipping today, V3 and V4, Broadwell, Haswell, to this new guy that hasn't got a number, that's got an abbreviation of SKL. And it's basically moving one thing that Intel is addressing, and that's the I/O bandwidth available per socket for packets processing, which includes not only the lanes, but also the buffering system that is in the PCI controller. Today, we are able to push up to 160 gig in and out per socket. In the future, short future, few months, we will be able to push 2 times 280 gig out of a theoretical 300 gig. So that's quite a big shift. And because so far we have proven that VPP limitation is really restricted in terms of bandwidth is per the PCIe I/O, we will be able to breach or go across the 1 terabit on the 2-socket server if you are a marketeer, because these bandwidths are TX and RX double, or if we're gonna get the 4-socket server out of the OCP, which is what they do, we will be able to get a proper 1 terabit technical terms on a single 2RU server. So that's quite impressive for all the network services on the VPP, and now we basically working with 100 gig NIC vendors to make sure that the NICs are good to go into those servers. Few more words about manageability aspect. VPP is very good at being managed over the binary APIs at 900K requests per second for API calls. We currently have one project that is making use of it, being an agent for NetConf RESTConf Young, and that's a Honeycomb agent. We have a new project that is starting, is being reviewed at FDIO this week or next week to be written in Golang to be much thinner as this one is developed in Java. The Golang is going to be smaller to address some of the smaller footprint requirements. Now, in terms of features, lots of Dataplane features. The software comes from Cisco networking company, so features are RFC compliant, as they've been shipping in Cisco products for a while. In terms of tunnels, you've got GRE, VXLAN, basically latest, greatest, including the GPE encapsulation, NSH, LTDV3 segment routing, V6, MPLS over Ethernet, GRE. Number of security things. One of the recent things we did was integrating of actually Intel team helped to write the CryptoDev drivers for the CryptoDev, the crypto accelerators, the quad cards, and now the software supports 100 gig crypto cards that you can basically proliferate in a server. The way that software is released is every 3 months, and you see some of the releases. 16.02 was the first one at launch, February 6.9.01, and 17.04 was actually happened yesterday. So I was updating the slides this morning. The release notes and images are available for downloading, and as you can see, we actually added quite a lot of features, including the latest CGNOT features from the written by the community. The way that software is being pushed and the patches being published, before the human actually looks at them, the data plane is being verified by a tiered way of CI/CD system. So there's a unit testing, there's a system functional testing done in a VM environment, and there's a performance testing that we run in SysIT to actually verify the performance and pick up any damages to the code. Then it follows to the code review by human committers and publishing artifacts on a per commit, per merge basis. So in terms of making use of VPP, it is a native software written for computers. It's been written from ground up. So this is not a retrofit of an existing software. You can use it as underpinning the infrastructure as a virtual switch. In a user mode, running server apps or VMs or containers. We just added a container interface. I need to speed up and finish the talk. One of the interesting things here is that it can also run within the VNF as a VNF in a VM. Equally, the same features, we can run it as a container. So we're looking to drive container use cases for network functions and anything that this entails. You can run it in embedded devices, CPEs, and you can. We have folks looking at putting the VPP software on their smart NICs on, say, ARM multi-core arrays. And then there are CPEs, whether they are physical or virtual. Most of the CPEs that you have at home are either Atom or ARM. So with that, this is my first slide and my final slide. So hopefully I gave you a sneak peek into what we mean by the most efficient on the planet. We actually do care about how the CPU microarchitectures are used and executed. And we have folks like Intel and others that are working with us to make sure that this is actually solid. And in terms of appeal to the community, try it, download it. It's all open source. The code is published, and we're looking for a set of applications for folks to help develop: firewall security applications, IDS, DPI, telemetry, and so on as per slides. And the Git repos and wiki pages are on the slide. So thanks very much.
Brilliant. I actually really enjoyed that. That was very, very informative. Thank you. I'm quite excited to actually see what you're doing. Do we have any questions for Maciek? Any at all? This would be great if we can get back on time.
Neil, you were supposed to ask a question.
Daniel, yes. He's first and fast.
Hello, Daniel Piekacz from Exanetworks. I've got a question about, have you tried, for instance, the Tylera platform with a really multi-core system, 70 or 100 cores based CPUs in that particular project?
What system, what microarchitecture?
Tylera.
What microarchitecture?
Tylera.
Tylera.
It's, there is a vendor like, for instance, Microtik, which is using that in CCR routers. It's a software-based router, which is using a CPU from a vendor called Tylera. Okay, maybe I pronounced it incorrectly.
Okay. What's the microarchitecture? Is it ARM or Intel?
No, it's
their own.
Yeah.
Then I don't know. Well, we in terms of supported CPU microarchitectures, as I listed, it's Intel x86, Xeon Atom, and derivatives. It's ARM. It's Power 8. And adopting to other CPU architectures is usually not hard, because they all follow the similar CPU core matrix and the cache hierarchy, but it requires compilation and some performance tuning, usually. So we didn't.
So the project is very heavily, I would say, dependent of the real core, each CPU core frequency, or it very efficiently use multi-core CPUs?
It does efficiently use multi-cores, but the higher the frequency, the more instructions you can execute, of course. So both dimensions.
Okay. Very, very quickly, Neil, if you can.
Yeah, I mean, so I think on that, the big issue is does the CPU have I/O? And it's only until, what's the latest, the CPU that you're using, Maciek?
The abbreviation is SKL.
SKL. Because without that, it scales, but doesn't scale quite as well. Other CPUs, they need to have good I/O.
Yeah, so with SKL, Skylake CPU, we're actually looking to get easily a quarter of a terabit per socket. And that's, we expect this to be a big game changer. Right, thank you.
Thank you very much, Maciek. Appreciate it.
Thank you.
Cheers.